In this video, we introduced a general workflow of ScopeSim by using a concrete example. A simulated observation of a star cluster with MICADO on the extremely large telescope. We do this based on a source defined through the ScopeSim templates. Along the way, we will adjust the detector window size, we will apply filters, change the exposure time, and look at the different modes MICADO can operate in. In our Jupyter notebook, we start by importing all the relevant packages. Import ScopeSim, and from the ScopeSim templates, we only need the Stellar cluster template, so we can import this directly. To quickly visualize the results, we define a very small function that simply plots the image data. For this tutorial, we will use the LMC cluster NGC1466 as an example. We will define the template source by using its parameters. A mass of around 140,000 solar masses, a distance of around 48.5 kiloparsec, and a core radius of 2.61 parsec. To generate a cluster from the templates, you can also pick a seed for reproducibility, but this is up to you. What this source function creates is a simple model of a star cluster, essentially a collection of point sources distributed according to the parameters we specified. On its own, this is just an abstract source. What we really want to see is how the structure would appear when observed with MICADO. To do that, we now need to define the instrument and the simulation pipeline that will be applied to the source. We call the instrument and detector packages we downloaded in the introduction video of this series. Simulation, with MICADO as our instrument. We will give it an exposure time of 180 seconds. And by this, we have told ScopeSim what instrument we are using. The corresponding instrument configuration and effects are then applied. Now we can take our source cluster and run it through the MICADO simulation. We do this by executing the simulation with the source as input. Once the simulation has finished, an HDU list is returned. With this HDU list, we have several options. One option is to save the result directly as a FITS file. This can be done by using the built-in AstroPy function write_to. After saving the file, it appears in our project directory, and you can now process it further using your usual tools. Another option, and the one we will use here, is to visualize the results directly in Python using matplotlib. We know from the HDU information that the imaging data we want to display is stored in extension 1. So we will select this extension as our image data and pass it to the plotting function we defined earlier. Here we can already see our cluster. By default, the simulation uses a detector window size of 1024 pixels. Depending on whether you're interested in individual stars or in the overall structure of the cluster, you may want to change this window size. We call MICADO settings, and we change the detector window size by adding the corresponding entries. For now, we will choose a fairly large window size of 8192 pixels, which allows us to see well beyond the core radius of the cluster. Feel free to choose a smaller window size here, and keep in mind that the larger the detector window size, the more memory it will take to run the simulation. After changing the detector window size, it is very important to run the simulation again. Anytime we modify the instrument settings, we need to rerun the simulation in order to obtain an updated result. As expected, this simulation takes noticeably longer to run. Once it's finished, let's look at the cluster again. We begin to see a structure, but the signal is strongly reduced by the active KS filter, which only transmits the near-infrared light. MICADO has two filter wheels, and while by default filter wheel 1 is open, in filter wheel 2 the KS filter is active. For visualization purposes, we remove the filter to increase the signal. We can modify the settings of filter wheel 2 by calling MICADO settings, selecting filter wheel 2 and setting the filter to open. After changing the filter settings, we run the simulation again. And let's see what it looks like. Removing the KS filter increased the detected signal, and now the cluster appears significantly brighter. Now that the cluster is clearly visible, we can look at it by using different instrument settings. Another default setting in the MICADO simulation is the adaptive optics mode and the imaging pixel scale. For imaging, MICADO provides two pixel scales, 4 milliarcseconds and 1.5 milliarcseconds. By default, the simulation uses MICADO's single conjugate adaptive optics mode, SCAO, together with the 4 milliarcsecond pixel scale. Both of these settings can be modified. For example, let's change the pixel scale to 1.5 milliarcseconds and let's run it again. We can now directly compare the SCAO images obtained with the 4 milliarcsecond and the 1.5 milliarcsecond pixel scale. You can see at 1.5 milliarcseconds, the point spread function is sampled much more finely, which makes the stellar profiles appear more detailed. Next, we switch the adaptive optics mode to MCAO and again inspect the result at a pixel scale of 1.5 milliarcseconds. For our cluster, the difference between SCAO and MCAO is relatively subtle, especially when using a smaller detector window. At the 4 milliarcsecond pixel scale, and with the filter wheel open, the broader MCAO point spread function becomes much more apparent. With this, we have explored how changing the detector window size, applying different filters, changing the AO mode and pixel scale affects the appearance of the simulated cluster. That's it for this video. In the second part of the cluster tutorials, we will import an actual image of NGC 1466 and look at it through MICADO.